So welcome to week number 15. This is lecture number, I think 28, because I'm uploading 24, 25, and 26. Maybe this is 27. I don't know, but it's the first lecture of week 15. And if you're joining us now after the fact, you can ignore all the writing on the side that was put there before we all got here. And I'm not sure what that all meant. It was very strange. It's like writing on the board when you walk into a classroom. You're trying to interpret it and you're like, oh, I wonder what the last class was discussing. That's all from the last class. So just ignore it. Okay, what we're going to do right now is we are going to jump ahead to chapter 20 on testing statistical significance. This is what it all has been leading up to. Okay, testing statistical significance. Now, I don't like this particular example, so we're going to skip it and we're going to do this one instead. Okay, example, Chernobyl and swallows. The 1986 accident at the Chernobyl nuclear reactor. I don't think any of you were old enough to remember Chernobyl, but I certainly was. I remember when Chernobyl.
It's that place that exploded in
Russia, yeah, somewhere in Russia.
Right,
nuclear radiation everywhere. And as we all know, or as I think we all know, nuclear radiation causes genetic mutations. So the accident at the Chernobyl nuclear reactor brought about concern that the radiation might cause mutations in the genes of humans and animals that would be passed on to offspring. Before the accident, 2% of barn swallows had white feathers in places where the plumage is normally blue or red. Why do they have white feathers? Because white feathers are caused by genetic mutations. As such, one way to check whether or not the Chernobyl reactor had a significant impact is whether or not the number of, or the percent of white feathers increased significantly. So in a sample of 266 barn swallows captured around Chernobyl between 1991 and 2000, about 16% had white feathers in places where the plumage is normally blue or red. So before the accident, it was 2%. And after the accident, it is now 16%. Okay, and the question is, the fact that it's 16%, is that within the realm of saying, yeah, okay, it's not the same as it was before, but I can see that happening? Can it be attributed to chance alone reasonably? Or is it what we call statistically significant? A statistically significant result is one whose outcome is so far away from what was expected that we have to truly question our hypotheses. Let me give you an example that's a little more familiar. If you flip a coin, what's the chances, assuming it's a fair coin, what's the chances of a fair coin flip that it's going to be a heads?
50%.
50%, okay, 50%. If you flipped a coin and got a heads, would you be shocked?
No.
No. If you flipped a coin twice and got two heads, would you be shocked?
No.
No.
Okay. How about 3 flips and 3 heads? Would you be shocked?
A little bit, but not significantly.
No, I don't think even it's enough to say a little bit. You might say, okay, wasn't expecting that, but I don't think you'd be like, my God, this can't be.
Right.
Right? But if you flipped 1,000 coins and got all heads, you would probably start to question whether the coin was fair in the first place.
Weighted.
Okay, yeah, but you would conclude it's either weighted, or maybe you would conclude that there's some mystical being who is manipulating it. I don't know whatever your conclusions are going to be. I think weighting is more scientifically sensible, but everyone has their own beliefs. There could be, the great turtle in the sky decides to play a role, who knows? The point is that if you believe it's a fair coin and you got 1,000 heads in a row, that is a result that is so unlikely that you need to question your belief about whether it was a fair coin. The same thing applies here. If we get a result of 16% when we expect a result of 2%, is that a result that is so unlikely that we have to question our belief of the validity of 2%? Or can it be attributed to chance alone? Do we say, okay, didn't expect that, but it's not crazy that it happened? Now, we don't have the math to determine the answer yet, but that's the goal of this section. The goal of this section is to understand the difference between questioning my hypotheses. In other words, the result is statistically significant. Or, okay, it wasn't what I expected, but I can see it happening, and therefore I'm not going to question my hypotheses. That's what we're going to be doing in this chapter, okay? Trying to understand how to come up with said conclusion. Does that make sense as for our motivation for this section?
Yeah.
I hope so. Okay. Now, in this past example, we have a few terms, a few values that we want to specify. One is the sample size. So when you read this example, what is the sample size?
Is it the 266 barn swallows?
It's the 266, right? That's your sample. You're not looking at every barn swallow in the universe. You're looking in it, and it even says the word sample, and a sample of them, right? So you're looking at n equals 266. P hat is the proportion of yeses in the sample. And when they say yes, they mean successes, or they mean some result, whatever result that you're after. So what is the proportion of successes in my sample?
Is it 16%?
It's 16, or it's approximately 16%, right? About 16% of the results in my sample had the thing that I was looking for, correct? Okay. Now, next, X is the number of yeses in the sample, the actual number. So if I had 16% of 266 barn swallows yeses, how do I determine the amount of yeses that I have?
Take 16% of 266.
16% of 266, which on my calculator is 42.56. And therefore I'm going to round to 43 because it does say about 16%. So we're going to assume that the about is 43. And then there's P, the standard against which the sample is to be compared. Our sample might be 16%, but what are we expecting is the actual value? What's the value that we're comparing it to for us to make 2%? Our conclusion? Huh?
Is it 2%?
I didn't hear that. One more time.
Is it 2% is what we're expecting to get?
Yeah, we're expecting 2%. Right? The P, the value that we are, this is not the P value, that's something else. The value that we are expecting in this case is 2%. So our value is 16%. The value that we're expecting is 2%. And then the question is 16% close enough to 2% that we say it's, oh, okay, I can see that happening? Or is it so far away that we say this is statistically significant result? Okay.
So Professor, X is 2%?
No, P is 2%.
X is 43.
X was 43. X is the actual number of yeses in the sample.
Okay, thank you.
Okay, 16%.
So P hat is
P hat is about
16%.
Yeah, if you want to be exact, it's going to be 43 divided by 266. It's going to be 16.17% if you want to be exact. But it's close enough. So in this picture, we have the following. Okay, and this is the basis for the entire chapter and what we're doing. So it's kind of important to really make sure you understand this. What we did is we took lots and lots and lots of samples of size 266 with a 2% expected proportion of yeses. In other words, we created a distribution of samples of the same size that we're dealing with the same proportion that we expect to have. We expect to have a 2% probability of success and a sample size of 266. And what we did is we took lots and lots and lots and lots and lots and lots and lots of samples, maybe 100, maybe 1,000. I don't know. We took lots of them. And what we did is we came up with this distribution right here. According to this distribution, which number is the most expected number of successes to have when we take samples of size 266 with a probability of success 2%. How many successes do we expect more than any other based upon this sample?
5?
5, right? The peak is at 5. 5 occurred the most times. And then 4 occurred a few less than 5, and then 6 occurred a few less than that, and then 3, and then 7, and so on. How many did we have again? I forgot. How many were in our sample? How many were in our sample again?
43.
43. In all of our thousands of samples that we took, how many of them had 43 successes, according to this little graph that we have here? How many of the thousands of examples that we took did we have 43 successes?
So would you have to look at where 0.16 is on the y-axis?
No, you look for 43 on the x-axis, because 43, the x-axis is a success axis.
Oh,
So how many times did we have 43 successes?
43 is not on there.
Yeah.
Yeah, 43 is on there. I'm gonna start moving the direction of 43. So let's take a look. Here's 0, 2, 4, 6, 6, all the way over there. All the way over there. That's 43.
So it's like this much.
Forget about that much. It never happens.
Yeah.
It never happened, not even once. So you're going to tell me that if 2% is really correct, it's reasonable to assume that you got 43 successes? It never happened. And yet you got it. So what do you conclude? You conclude it must never have been 2% in the first place.
Okay.
Because if it's 2%, it would never happen. And yet it did happen. So you have to really question your hypothesis.
So because of the 2% not being it, would the percentage have been higher?
So wasn't that the whole point, that we're trying to determine whether or not Chernobyl caused more genetic mutations? And the sample that we got seems to indicate that 2% is too low and the true value is now higher.
Okay.
Do I know that the true value is 16%? No, I don't know that. But I do reasonably conclude that it's bigger than 2%. This is the idea. This is the entire idea. If it really is 2%, we would expect something that looks like this. And if we get something that looks like this, we are never getting 43 successes. But we got 43 successes. That's what actually happened, which means it can't look like this. This part here must not be correct. Must not be correct. It could be the worst sample taken in the history of time. We happen to get a sample of 43 successes. Wow, that was a bad sample. I mean, theoretically it's possible, but it never happens in all of our samples, which means it's so unlikely that we really have to discount it. Now, in all of these examples, what was the size of each sample in this distribution? What was the size of each sample in this distribution? Every one of them was the same as our sample size. Every single one of them was a sample of size 266. It makes no sense to talk about any other size sample. How can I compare a size 266 sample to a size million sample? Of course, a size million sample is going to have more successes. It's a bigger size sample, right? So I can only really look at size 266 samples if I want to compare it to my size 266 sample. What value of P was used to construct it?
2%.
2%.
2%. Okay, good, excellent. Keep going.
Like 2% of 266?
No, take the next one, 2%. All right.
Okay.
What does the bar above the 4 represent?
That I was trying to find. What is it talking about?
The bar above 4. So this is the bar above 4. What is that?
Oh, the whole bar.
4?
I don't know. I was looking for like something else. I was like, what?
No problem.
Okay. The bar above the 4.
What does
So
the bar above 4
bar?
represent, huh?
The 5 bar? Or like
It represents what exactly? It represents that we had 4 successes. What proportion of time? what proportion of all of our samples that we took, and we took lots of samples, what proportion of them did we get 4 successes?
17% of the time.
About 17% of the time. 17%, 16, whatever it is, of our samples were 4 successes. Does that make sense?
Mm-hmm.
What is the mean of this distribution?
Would it be about 5?
Well, the peak is certainly at 5, correct? So it seems that the mean of this distribution is about 5. Okay, so we expect to have roughly 5 successes per sample. To get 43, yeah, go ahead.
And that's if we had 2%.
And that's
Right.
if the true value is 2%. Everything we do is based upon our hypotheses, and our hypotheses are that it's 2%. If it's 2%, this is what we expect. And we got nothing near here, which is why we start to question the 2%. Does that make sense?
Mm-hmm.
We got to really question this. If it's so unlikely that we'd have 43 successes, and yet we got 43 successes, there's got to be a disconnect somewhere, all right? And that's exactly what we're trying to do. Okay, so now, what is the largest number of birds with white feathers that it is possible to get in a sample of size 266? Not that we actually got, but that it's possible to get. If I have a sample of size 266, what's the most number of birds that I can possibly get with white feathers?
All of them?
All of them, which is how many?
266?
266, right? So the largest that I can possibly get would be 266. But based upon the picture, what's the largest that is plausible to get? You have to kind of decide what percent you consider to be plausible. If it happens 1% of the time, is that really plausible?
No.
Okay, so which number would you say here is the largest plausible value that you might possibly have gotten?
17?
17 is way out here. 17 is off the chart.
Oh, sorry.
That's very unlikely, right?
Are we looking at the X values?
Well, yeah, we're looking at which X value is the largest plausible X value.
5?
About 13.
Well, 1 second. Let me first address 5. 5 is the most expected, but would you, if you got 6, would you say, this is crazy, this is not possible?
13?
No, so 6 is still plausible. 7 is still more than 10% of the time. That's still plausible.
So 13.
I'd probably say 10. I'd say once you get under 5%, I'd say once you get under, yeah, especially this is very low. 2% of the time it happens. If you got a result 2% of the time and it happened, would you think that was a very plausible result?
No.
No. So I would probably say 10 is probably the largest plausible result to get.
Okay.
Maybe 11, but somewhere certainly in the vicinity of 10 or 11 is the
And
most
that's because
plausible.
it's above 2% on the graph.
Yeah, I mean, you got to ask yourself, what's the limit of plausibility, right? I mean, listen, when we did p-values, what was our cutoff for p-values? Well, it was always 5%, right?
Mm-hmm.
If something was less than a 5% chance of happening, what did we say? We said that this is an unlikely result, and therefore we don't count it, right? So I would say the same thing here. Once you drop beneath 5%, it's already you're on the border of implausibility. Maybe even 9 is the most plausible. I mean, it's 9, 10, somewhere around there. Now, place an X where the result from the actual sample was located. The actual sample, where is that located? What value did we get in our actual sample?
43.
43, correct? So let's place an X by 43, which is over here. I don't even think that's enough to get there, right? 43 is way off the charts, correct? So look at the last question. This is the goal. What approximately is the probability of getting 43 or even more than 43 birds with white feathers if you are selecting 266 birds at random from a population where 2% have white feathers. It is approximately 0%. It is so unlikely as to essentially never happen. This is called the p-value. Okay, the p-value is the probability of getting the result that you got or something even more extreme, even further away. If that probability is really, really small, you seriously have to start questioning your hypothesis. Does that make sense?
Would we even say that 14 is approximately 0%?
Yeah, 14 is already approximately 0. So let alone 43 or more. I mean, that's so far out there, right? So this is the big one. The p-value is the probability of getting a result from a random sample as extreme or even more extreme than the one from the actual sample. In other words, the probability of getting what you got or something even more unlikely if P was correct. If the belief on P was correct, the p-value is the likelihood of getting what you got. If it's less than 5%, we consider it quite unlikely to get a result with that value of P. The result is said to be statistically significant. And as a result, we start to seriously question whether the value of P that we're assuming is correct. In our example, I would come out of there saying P is not 2%. Because if P was 2%, I never would have gotten 43 successes. It's just too unlikely of a result. And therefore, I'm going to conclude that P is really higher than 2%. How high? That I can't tell you. But it ain't 2%. That would be the results. So in this case, we say it is a statistically significant result. It cannot be attributed to chance alone. It's too unlikely to be attributed to chance alone. Think of winning the lottery like 5 times in a row.
Cheating.
Okay, that is so unlikely that if it happened, we would seriously question whether or not you did something that you did not act inappropriately. You didn't cheat or hack into the system or something like that.
So can I ask a question? I'm
No.
kind of having a hard time with this, but
Yeah.
so was the original like 2%, was that information faulty to begin with? Like,
Well, it's not that it was, well, yes. Your conclusion is that it was faulty. Your conclusion is that it cannot be correct because if it was correct, this result is not possible, or at least not plausible.
okay.
Okay, so we are going into this saying, I think P is 2%. Really? You think it's 2%? Let's take a sample and test it. I got 43 successes. If it was really 2%, I would have gotten 43 successes. Oh, okay, then maybe it's not 2% after all.
Mhm. Okay.
So does the study provide convincing evidence that there was a higher rate of these mutations after Chernobyl? Yes. Okay, after Chernobyl, it jumps. It's no longer the 2% that it was before. So yes. So here's another one. Test of the validity of natal charts. Who here is a believer in astrology? No judgment, I promise. Oh, sorry. Okay. Well, there are people who believe in astrology, and that's fine. My personal belief as a Jew, just so you know, is that the Jewish religion believes that people back in the day were able to divine certain things from the planets and whatnot. We believe that skill has been lost over time. So we have this belief that such a thing did exist at one point in time. Just if you came to me nowadays and said, yeah, I have a friend who's really good at this stuff, I'd be like, yeah, I don't really believe it. Even though I believe that such a thing might possibly exist. That's my personal belief. So I really don't care if you believe it or not. You believe whatever makes you happy. But let's see what happened here. Professional astrologers prepared natal charts for 83 volunteer subjects. Now, the professional astrologers prepared these charts and then gave each person 3 charts. The one that they prepared and 2 others, 2 random others. So each person now has 3. And then those people were asked to pick out the one that most correctly described them. Now, if you're given 3 charts, okay, and these astrologers just have no idea what they're doing, so that all 3 of these are complete nonsense, then what percent of the time do you think a person would pick their own charts by accident? You have 3 of them. What is the chance that you pick yours?
1 out of 3.
1 out of 3. Right? Even by accident, you're going to be right 1 out of 3 times. So P in this case, the thing that we're testing, the standard for which we are going to compare our results is 0.333 and so on, 1/3. This is the result that we are going to test against. Is it really 1/3? Or are these astrologers really good at what they're doing and it's really more than 1/3? So what is our sample size?
83 volunteer subjects.
83 volunteer subjects. So the sample size is 83. How many yeses were there in our sample? How many in our sample were yeses, were correct? I didn't actually read it out loud, but you guys can do that. How many in our sample are actually correct?
20.
How many?
Was it 28 out of 83 selected their own chart?
Yeah, so 28 out of the 83 selected their own chart. So what is the proportion of yeses in our sample?
28 divided by 83.
Which is how much?
Which is 28 divided by 83 is 33.73%.
Okay. So if we expect a result of 0.333 and we got a result of 0.337, are we going to say, oh, 0.333 can't be right? There's no way. Is that your conclusion?
No, it's super close.
It's super close. It's super close. The standard that you're comparing it to is 0.333. It's super close, which means that what would you conclude based upon the results of this sample? Would you conclude that it's really higher than 0.33? Or would you say there's not enough evidence to conclude that it's really higher than 0.333?
Not enough evidence to
Not
come.
enough evidence.
There's not enough evidence. Our result is so close to 0.333, you can't discount that as a possibility. And therefore, the results of this sample would seem to indicate that professional astrologers are no different than random chance.
Mhm.
Now, I don't know, this is an actual study, by the way. This is an actual study. This is not like a made up situation. 1985, that's probably before most of you were born, I would think. Not you, though.
Well,
So, Professor,
Yeah.
like the wording on page, would we say that it can be reasonably attributed to chance alone?
Sorry, say it again. I'm sorry. What?
The wording on page 6, for when you circled whether it was statistically significant, would we say that it can be reasonably attributed?
Yes, it can be reasonably attributed to chance alone. Exactly. This one is not statistically significant. Who wrote something? 87 LOL.
That means 1987.
Oh, that's when you were born, 1987? Gotcha. That's still younger than me. All right. So here is the sampling distribution for this particular situation. Okay. We took samples of size what? All of these examples are samples of size what? Every single one of them, huh?
83.
Not, where do you get 36 from?
83.
83, right? The size of all of our samples is 83. Every single one of them has a size 83 size sample. And what is the assumption of our P for this distribution?
0.333.
0.333. If it really was 0.333, where would the center of this be at?
A little skewed to the right.
No, but what number?
Oh,
If we really expect 0.333, that proportion of my 83 size sample, then where do I expect the center of this distribution to be located?
0.045-ish.
What number?
You said 33%? Or 0.33?
33% of 83 is how much?
oh,
Oh. That one.
What is 33% of 83?
I need to calculate.
27.39.
27.639, right?
0.39.
Did you do 0.33 or 0.333?
Oh, I left 1 3
Okay.
out.
That's okay. 27 point something. Does the peak seem to be at 27?
Yeah.
Okay, so that seems reasonable. Now, what was our result again? What proportion of ours were successes? I forgot.
28.
So let's put an X by 28. Is that a reasonable outcome, 28? Do we get that and we say, what? That's crazy. Or do we say, okay, that's perfectly reasonable, expected.
It's a reasonable outcome.
It's a very reasonable outcome, right? In fact, what's the smallest reasonable outcome based upon this chart? What do you say is the smallest reasonable outcome?
You said anything above 5%.
Yeah, let's say 5% is the cutoff. So if 5% is the cutoff, what's the smallest reasonable outcome?
Probably like
24.
23-ish, 20.
Well, here's 24. 23 is still above 5%. So about 23, give or take, I would say. Right? 23 seems to be roughly the smallest reasonable outcome. What's the largest reasonable outcome, by the way?
28.
No, 28. 29 is still reasonable. 29 to 9% almost.
Oh, okay.
What's the highest reasonable outcome?
About 34, 33.
34 is already underneath 5%. 33 is underneath 5%. 32 is above. Yeah, so I would say 23 to 32. Anything in that range would be a plausible outcome. Anything in that range is a plausible outcome. Did we get something in that range?
Yes.
Yes. So therefore, our result is certainly plausible. Because our result is plausible, when we get here to the end, and it says, is the result statistically significant or can it be attributed to chance alone reasonably? What is our conclusion? Is it a statistically significant result where we doubt our hypothesis, or can it be attributed reasonably to chance alone?
The latter.
The latter. So this one can reasonably be attributed to chance alone. So does the experiment provide convincing evidence that a person's own chart describes them better, in their opinion, of course, than randomly selected ones? The answer would be no. Because our result seems to jive with pure randomness. Does that make sense?
Yep.
Yeah. So here's a nice little example. Chimpanzees were given the choice of pulling one of two heavy rakes toward them. Pulling one of the rakes would bring food with it, and pulling the other one would not. And it was always randomized. So they didn't get in the habit of always, the right one always had food, because then they could just, that's a lurking variable. The researchers found that the correct rake was chosen significantly more often than would be expected by chance alone. And they had a p-value of 0.01. Okay, their p-value, the likelihood of getting a result as extreme as their own or even more extreme was 1%. So first, what is the standard against which the sample was compared? They don't say it in the example. You have to use a little common sense here. Okay? If it was purely random and the chimpanzee would have no reason to pick one over the other, then what percent of the time would the chimpanzee pick the one with food?
50%.
50%, right? So unless we have reason to assume otherwise, the standard to which we're comparing is straight up 0.5. So what is the p-value? Can someone interpret the p-value in this particular problem? What is the p-value?
Doesn't it tell us the p-value?
Yeah, I'm not saying what is it. I'm saying interpret it. Interpret the p-value. So the answer is the chimpanzees picked the correct rake so often that the chance of them picking it that much or even more was less than 1% if p was really 0.5. Now, if p was really 0.5 and something had less or something had a 1% chance of occurring and actually occurred, what do you say about 0.5?
That it's pretty accurate.
Just the opposite. If there's a 1% chance that something occurs when p is 0.5 and it actually occurred, are you going to sit there and tell me that 0.5 seems reasonable?
No.
You seem like you're guessing here. You seem like you're a little unsure. A little bit unsure. Again, if p was 0.5, there's a 1% chance of getting the result that we got. And yet that's the result that we did get. Does p equal 0.5 seem reasonable based upon that?
I'm just having a hard time understanding it. So when p is 0.5, does that mean that half of the time
No.
the chimps?
No. P is 0.5 means we believe that half the time the chimps are going to pick the food. The standard at which we're say again.
So then, but it actually occurred 0.01%?
No.
Or 0.01?
Again, there's two different things here. Two completely different things here. The p, the standard p, is the value that you're going to compare your results to. In other words, we are going into this experiment assuming that the chimps are going to pick the correct rake half the time, 0.5 of the time. We got a result that would only occur 1% of the time if that were true.
Oh.
If p
So it
was
wouldn't be reasonable.
It doesn't seem very reasonable because 1% of the time to get a result and it happens, we got to seriously question whether p equals 0.5 was really true or not.
I see.
Okay.
Can we get 50%? Can we get 50% because of the 2 rates?
Yeah, that's exactly where we got it from. That's exactly where we got it from. Okay. In other words, there's two different things going on here. P is the assumed value that we're testing. The p-value is the likelihood of getting the result that you got if that were true. This is the result that has a 1% chance of occurring if p was really 0.5. And yet it happened. That's our result. Does 0.5 seem reasonable then? If we're only going to get a result 1% of the time if p was really 0.5 and that's the result that we got. No, it does not seem reasonable. It's too unlikely. It's too unlikely. So what do the researchers conclude? They conclude that the chimpanzees seem to be able to recognize food. Or at least recognize that this process of picking the one, that this rake process is a way to get their food to them. It's not so obvious a result. I mean, I know we know now that chimpanzees are rather intelligent on the animal spectrum, but I can tell you right now, I went to Thanksgiving at a friend's house and he had a dog and I held the dog up to the mirror. I'm like, hey, look at you, look at the dog. dog. And the dog's like, they don't see anything. Dog can't recognize himself. Dogs are stupid. Right? So just because we, would obviously recognize, oh, there's food. Let's pull the food towards me. Does not automatically mean that chimpanzees are the same, which is why they did this experiment. But dogs really are stupid. They just bark at anything.
So Professor,
No.
Yeah, they are. My dog is so smart. She can sit up when I say sit. Wow, that makes her smart? No, it makes her trained.
They gotta be
Sorry.
trainable.
It's debatable, really?
No, they have to have the capacity to understand that command, so they are smart.
Okay, so our definitions of smart are maybe not exactly the same, but nevertheless. Okay, significance testing in education. Here we go.
Professor,
Yes.
so for the last slide, the second question is that the P is too unlikely.
The p-value is so small that our assumed value of p is unlikely. To get a p-value less than 5%, we seriously question whether or not our assumed value is correct. In this case, our assumed value was 0.5. We question the validity of 0.5 because the result that we got does not seem to really, jive is really the best word. I can't think of a better one. It doesn't really jive with that. And therefore, the researchers conclude the true value of p, which we still don't know, is somewhere higher than 0.5. Maybe 0.8, maybe 0.9, I don't know. Here's another example. California tests all fifth grade students on physical fitness. 63% of fifth graders have an aerobic capacity that is considered healthy. Now, your principal at your school says, okay, well, let's test our school. So he grabbed or she grabbed 65 fifth graders, and 30 of them were considered healthy. Is this difference statistically significant? Is this result?
Would it be no, because it says the 63% of fifth graders, but what we got was 19.5% out of our sample.
Well, this is not 19.5. 30 out of 65 is not 19.5. Is that what you got for 30 over 65?
30 over 65 is 46%.
Is 46.
Oh, 46. Sorry.
So the proportion in our sample is 46%. You can use 0.46 or 46%. The number of yeses in our sample is 30. The size of our sample is 65. We're comparing it against 63%. So the question is our value of 46 so far from 63 that we want to question whether 63% is correct?
Maybe kind of.
Well, let's take a look. Let's take a look. Here's our graph. We took samples of size 65, lots and lots of samples of size 65, all of whom have a probability of success 0.63. And this is our distribution. So what is the largest number of fifth graders that is possible to get in a sample of size 65?
65.
65, all right, all of them.
Mm-hmm.
What's the smallest number?
0.
0. It could be none of them. What's the largest plausible number based upon our 5% rule?
5%, is that 46?
Let's take a look. 45 is still good. It's higher than 5%.
Oh, 46
seems lower, so 45 seems the highest plausible number. What's the smallest plausible number?
It looks like 37.
Looks like 37. What was ours again?
Our percentage?
No, our number. It was 30,
Oh,
right?
30.
Does 30 seem plausible?
30.
No, it's lower than the lowest plausible.
That's right. It does not seem plausible at all, right? In fact, what approximately is the probability of getting 30 or even fewer? It looks like it's, here's 1%. It's very close to 0%. Right? It's very close to 0%.
Yeah.
Right? The name for this probability is called the p-value. That's what we call it. Is this result statistically significant, or is this result not statistically significant?
Statistically significant.
It is a statistically significant result. It cannot be attributed to chance alone. It's a statistically significant result. So, as the principal of your school, what do you conclude?
Test more kids.
Sorry, what?
Test more kids.
Not test more kids, because your sample is a good sample. You could test more kids, but let's assume you'll get the same result.
That your school's kids generally have low aerobic.
Yes. Yes. Yes, exactly. I don't question necessarily the California value. Oh, 63% can't be right because my kids are not like that. It's probably more sensible to say, I better up the physical education regimen in my school because my kids are fat, or my kids are slow, or my kids are just whatever the case may be. I shouldn't make fun. I'm not making fun. I shouldn't use that word. I find that in our generation, most things you can't make fun of anymore. When I was growing up, everything was fair game. Religion, race, everything. That's just the way we were. We didn't know any better. We know better now, right? We're more educated. We're more sensitive to other people. But we weren't like that when I was growing up. It's a very different time. But obesity still seems to be the one thing that people feel they can get away with making fun of. And being obese myself, I should really be leading the way and not doing that myself. So I do apologize. But nevertheless, that is the result that we conclude here.
What was the last part again?
So what would I recommend to the teachers at your school? Have more physical education, get their aerobic values higher, whatever you got to do. Does that make sense?
Yeah, thank you.
Okay, now one last example, just so you know, this is an actual case before the Supreme Court. A person was convicted, and he actually had his either conviction overturned or possibly he got a new jury. I'm not sure exactly the details, but here's the situation. A 1977 U.S. Supreme Court, Castaneda versus Partida, was explicitly decided on statistical evidence. Okay, a grand jury decides whether a person will have to stand trial. Of the 870 persons who were summoned to serve as grand jurors in Hidalgo County, Texas, over an 11-year period, 39% had Spanish surnames. However, census figures showed that 79% of the county's population had Spanish surnames. So he was convicted of a crime and he appealed, because he said it was racially biased. If the true proportion of Hispanic people in my community is 79%, for me to have a jury of 39% means, yes, it could happen, but is it likely, is it plausible to happen? Is the p-value so small that I was given an unfair trial because I had a significant proportion of jurors who might not have empathized with my situation? Okay, so in our example, what's the sample size?
870 people.
870 people. That's my sample. 870 people. What's the proportion of yeses in my sample?
39.
It looks like 39%. How many yeses were there in my sample?
339.
339. And what is the standard against which my sample is to be compared?
Was it 79%?
79%. So when I make my distribution of samples of size 870 under the assumed 0.79 proportion, how many of those had 339 successes? How plausible is it?
Zero.
Zero. It never happens. It is so unlikely as a result that it should never happen. The only way it could happen is that there was a flaw in the grand jury selection system. And he felt that he was convicted via this flaw. And the case was actually, I don't know if it was overturned or if just was appealed. He appealed. And it doesn't say what the eventual outcome was. But I would be interested in knowing. That's an interesting case. Anyone want to look it up? Castaneda versus Partida?
Doing it.
Doing it. And that's the end of the lesson today. So we can, we can just do that and then we'll be done with it. So what does it say? Does it show up there?
I don't know. I'm looking.
That's okay. Anyway, that's the point of today's lecture. Okay, the point of today's lecture is the idea that you have a belief going in, you take a sample to test your belief, and then you compare the results of your sample to what you expect to get if your beliefs were really true. And from that, you come up with a conclusion about whether or not the result is statistically significant, so that you reject your underlying beliefs, or whether it's not statistically significant if it can happen by chance alone, in which case you continue with your underlying beliefs. Does that make sense? Yes, no, maybe so? And then here's a picture of lots of little dolls and stuff. So that's always going to make people happy. I mean, who's not happy with dolls and stuff? Right? Okay, so I'm going to stop sharing. Are there any questions with today's lecture? If you have not yet done so, I'm going to let you guys out 14 minutes early, but if you have not yet done so, I think I talked to someone before, Talar, and she confirmed. I did mention, I'm going to stop recording, but I did mention that you guys